Hi, question 7 here. It is a nonlinear regression model. We are assuming the mean independence assumption and this additional assumption. By the way, I think I did not explain what this means. Almost surely. So almost sure is what it means. So let me explain. It says theta 0 is the only value that satisfies this, right? Right. So the condition is this one. And as you see, this is, as I keep repeating, this is a function of xi. So let me write this whole function as, say, fxi, right? So this is a function of theta. So I'll write it as fxi comma theta, and it should be 0 only when theta equals to theta 0. Then what happens to the argument x? Okay, so what we want is what we want to say here is when theta equals to the true value, this holds with probability 100%. Okay, that's what we want to say here. So let me erase all the things. And what you want to say here is theta is the only value that satisfies such that expectation of yi minus gxi theta given xi is 0 for 100%. Okay? So what this means is, for example, when you think about a function g, if you think about a nonlinear function or a very weird function, so for example, suppose that xi is normal distribution, for example, and what is the probability of xi equals to, say, 100, for example? Its probability is 0. Okay, 1 point does not matter in terms of the probability. So we don't need to restrict all possible values. We just need to make sure the probability is 100%. So this means, almost surely means, we don't care about the values that has 0 probability. Okay, for example, like say, suppose that we are thinking about a function that has a jump at a certain point. For example, like say g x theta equals indicator function x greater than theta. Okay, so then it has a jump at a certain point, but so think about two different cases whether so it could be x strictly greater than theta or x greater than or equal to theta. So mathematically, these two are different functions, but probability wise, we don't care. So this point may be here or there, it does not matter because 1 point has 0 probability if the random variable is continuously distributed. So for rigor, I put it this way. But if you have difficulty with that, I don't mind even if you don't care about that. So I say that, like say first, then the first part A, we have to show that theta 0 is the unique minimizer. So q theta is defined as probability yi minus gxi theta squared. Okay, this way. And for simplicity, I am going to write gxi theta in this way. It is just gxi theta. X does not play any role here, so I'll just simplify the notation using subscript I directly on the function g. And then for theta tilde, that is different from theta 0, I want to show that theta tilde, q of theta tilde minus q of theta 0 is strictly positive. Okay, how can we do that? Theta q theta tilde is expectation yi minus gi theta tilde, and q theta 0 is yi minus gi theta 0. Okay, by the functional form assumption, we can rewrite this as, so y is gi theta 0 plus ui minus gi theta tilde square. And here it simplifies to ui squared. So simply ui is replaced by gi theta 0 plus u. Okay, and then the q theta 0 can be written as, okay, let me continue here. It can be written as probability expectation ui squared. I will write it first and then just expand it. 2 times expectation gi theta 0 minus gi theta tilde times ui. This is cross product plus expectation gi theta tilde minus gi theta 0. The order does not matter here. Okay, g actually 0 minus theta tilde, it is squared. Okay, let me be more rigorous. Theta 0, theta tilde. Okay. Okay, now then, let's think about the second term. The second term, we use the law of iterated expectations. So because expectation of ui given xi is 0, and we know it equals expectation of expectation gi theta 0 minus gi theta tilde ui given xi. If you take this, then conditional on x, these two guys are constant. So they get out of the expectation. So we have this form, and this part is 0. Okay, so this is whole 0. Whole term is 0. Okay, and then let's think about q theta tilde minus q theta 0. Then this term is cancelled out by this, so they go away. And in the end, we only have gi theta 0 minus gi theta tilde, and it's square. And obviously, it should be always positive because there is only, the theta 0 is the only value that satisfies this equation. So that means theta tilde should be non-zero at some point with positive probability. So squared expectation, the variation, should be strictly positive. Okay, that was part A. Now let's think about part B. So assume that g is twice differentiable with respect to theta. Show that the first derivative should be linearly independent for theta 0 to be a minimizer. Okay, so as you can expect, it is about second order condition. Okay, so let's first calculate the first derivative, which I am going to write it as q prime theta for simplicity, right? Derivative. derivative is minus 2 times expectation gi theta times yi minus gi theta. I'm using the same notation as before. Gi means x is included in the notation. Okay, this is first order derivative, and second order derivative is, differentiate this once more, 2 times expectation. If you differentiate with respect to the second term, gi theta and gi theta, g theta transpose, partial theta transpose. And if you differentiate with respect to here, then minus 2 times expectation g squared, partial square delta square gi theta and g theta, partial theta transpose times ui minus gi theta 0. Okay, that's a second derivative. What we want to do here is, like, this is possible because we assumed the second derivative exists. Okay, and for theta 0 to be a minimizer, we know that this should be convex. So this should be, the second order condition should be true at theta 0. It means even if globally Q may not be convex, but even if like it's not convex, but so around the minimum, right? Even if it's local minimum, it is convex locally, right? So then it is at least a local minimum, okay? So we would like to show this one. So then what we have to do here is we have to plug in theta 0 here, 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 here. Okay? So this is a function of theta. So we plug in theta 0 to theta. And then the second term, let's look at the second term first. The second term, we use the law of iterated expectation again. Expectation of, let me simply write second derivative this way. This equals expectation of gi dot dot theta 0 times ui. Okay? That means we may use the law of iterated expectations again to simplify. Then we know the second derivative of g depends only on x, so it is constant when x is conditioned, like this, and we know it is 0, so it equals to 0. So second part equals to 0. That is pretty simple. And here we only care about this. And like in a previous question, we learned that when this is strictly positive definite, it is equivalent to its invariability. Invariable. Okay, so same thing holds here. In this case, it should be strictly positive for the function to be convex. That means it is strictly positive, right? So g prime theta 0 and g prime theta 0 transpose should be invariable, which means it is full rank, which means each of the columns or rows are linearly independent by definition. Okay, so that's the proof for the second condition. Now the third one, it is pretty simple. we have expectation of ui given xi is 0. Then we want to show expectation of xi ui is also 0. So this is uncorrelatedness, and this is mean independence, conditional mean independence. Conditional mean independence implies uncorrelatedness. It's pretty simple. Law of iterated expectations again. Okay, and then this is 0, so it is 0, right? So uncorrelatedness is more general, mild, and mean independence is more stronger and more restrictive. Okay, so this is how we prove that. And the last question here, show that the results above do not hold when we relax the assumption of the mean independence to uncorrelatedness. That is because that's because we had to show that, like for example, we are using law of iterated expectations here, and also we are using the similar technique here. Okay, so for example, I'm sorry, gi 2 prime theta 0 ui, we need to show this equals to 0. But uncorrelatedness does not imply this, right? For example, like xi ui is 0, or covariance is 0, correlation is 0, still expectation of say xi squared times ui may not be 0. There is no guarantee, right? So there is no direct, we cannot apply the law of iterated expectation. Law of iterated expectation is not applicable to nonlinear function. In other words, the covariance or the correlation coefficients are only about linear relationship, right? So even if you assume covariance is 0, that only implies there is no linear relationship, but there might be nonlinear relationship might be different. So that is not enough.